So what I'm actually going to do is read from a chapter in my book, and it's written, so just keep in mind, so the book that is called Knocking on Heaven's Door. It's actually called something different in German, and I don't remember the German title, which is terrible. But it was basically about the nature of science and also about the physics I was about to start at the Large Hadron Collider. I wrote it before the Large Hadron Collider had started. So it's geared towards understanding the nature of science and using the actual science as examples. So in there, and it's in part, it's a response to the fact that there are a lot of debates that you hear, especially in America, but other places too, about, mistrust of science or what science is. And I think the scientists end up, I think the people who are objecting to science are wrong, but I think the scientists sometimes present an overly simplified view of what science is. And so you lose the messiness that happens when it's actually going on. And so I want to write it from the perspective of someone really doing science and what it really looks like. So I really appreciated the thoughts, not just about symmetry, but about the breaking of symmetry, which is a really important concept in physics. And it's something that I had a couple of chapters about there. And also, there's a notion of effective theory, which I'm not going to talk about now. But for now, I'm going to just read you not all of it, because of lack of time, but the chapter that I called Truth and Beauty and Other Scientific Misconceptions. And it's actually very funny, because when I went back to look at the PDF of my book, I realized, I was pretty careful about checking the copy edits, but I realized one of the copy edits had been to change it to Truth, Beauty, and Other Scientific Misconceptions, completely missing the idea that it was really the unification of truth and beauty that was really the thing I was talking about. And just to give you some background, this is not from the actual chapter, but and I think, again, Thomas went into this a little bit, when we're actually doing science, we're doing theory, we're trying to extrapolate for what's going on, we need some guiding principles. We're not starting in a vacuum, but you have to decide which way you're going to go forward. And what are the guiding things? Well, of course, primary, we'd like it to be experiments, but we don't always have experiments at the energies, at the sensitivity that we want. Inconsistencies is another thing that will drive us. If we have a theory that seems internally inconsistent, that's definitely a sign that something's wrong, and that will often drive us forward. Introduction of new methods. Sometimes we'll find something that works in some context. So even if you're not a string theorist, there might be some new elements or ingredients or methods that come out of string theory that will help us address our science, which happens sometimes. But of course, the search for beauty is often stated as one of the key driving factors. And I would agree that the search for economy and simplicity is part of what we do, but I am not extraordinarily happy about the idea of truth and beauty. So this is the chapter I wrote about this. Okay. So it starts in February 2007. It's actually the same example Thomas used. The Nobel Prize-winning theoretical physicist Murray Gell-Mann spoke at the elite TED conference in California, where innovators working in science, technology, literature, entertainment, and other forefront arenas gather once a year to present new developments and insights about a wide variety of subjects. Murray's crowd-pleasing talk, which was rewarded with a standing ovation, was on the topic of truth and beauty in science. Murray's basic premise can best be summarized by his words that echoed John Keats. Truth is beauty and beauty is truth. Gell-Mann had good reasons to believe his grand statement. He had made some of his most significant Nobel Prize-winning discoveries about quarks by searching for an underlying principle that could elegantly organize the seemingly random set of data that experiments discovered in the 1960s. So it's a little bit reminiscent of what we just heard, where you have this big set of data, it seems to be nonsensical, but then he found this underlying organizing principle, which in some sense might be considered to be DNA in that case. In Murray's experience, the search for beauty, or at least simplicity, had also led to truth. No one in the audience disputed his claim. After all, most people love the idea that beauty and truth go together and that the search for one will more often than not reveal the other. But I confess that I've always found this assumption a little slippery. Although everyone would love to believe that beauty is at the heart of great scientific theories, and the truth will always be aesthetically satisfying, beauty is a subjective criterion that will never be a reliable arbiter of truth. The basic problem with the identification of truth and beauty is that it does not always hold. It holds only when it does. If truth and beauty were equivalent, the words ugly truth would never have entered our vocabulary. Even though those words weren't specifically directed towards science, observations about the world are not always beautiful. In fact, Darwin's colleague, Thomas Huxley, and I think that we'll hear a lot about this tomorrow, nicely summarized the sentiment when he said science is organized common sense where many a beautiful theory was killed by an ugly fact. To make matters more difficult, physicists have to allow for the disconcerting observation that the universe and its elements are not entirely beautiful. We observe a plethora of messy phenomena and a zoo of particles that we'd like to understand. Ideally, physicists would love to find a simple theory capable of explaining all such observations that uses only a spare set of rules and the fewest possible fundamental ingredients. But even when searching for a simple, elegant, unifying theory, one that can be used to predict the result of any particle physics experiment, for example, we know that even if we find it, we would need many further steps to connect it to our world. The universe is complex. New ingredients and principles are generally needed before we can connect a simple, spare formulation to the more complicated surrounding world. Those additional ingredients might destroy the beauty present in the initial proposed formulation, much as earmarks all too often interfere with congressional bills' initial idealistic legislation. Given the potential pitfalls, how do we go about trying to go beyond what we know? How do we try to interpret as yet unexplained phenomena? So what I'm going to talk about is the idea of beauty and the role of aesthetic criteria in science, and it will consider the advantages and disadvantages of beauty as a guide. And I'll also talk about model building, which is what I do, which uses a bottom-up approach to science while paying attention to aesthetic criteria and attempts to guess what comes next. Okay. So this subsection is called beauty, and it starts, I recently spoke with an artist who humorously remarked how one of the great ironies of modern science is that today's researchers seem more likely than contemporary artists to present beauty as their goal. Of course, artists haven't abandoned aesthetic criteria, but they are at least as likely to talk about discovery and invention when discussing their work. Scientists cherish those other attributes too, but they simultaneously strive to find the elegant theories they find most compelling. Yet despite the value many scientists place on beauty, they have divergent notions about what is simple and beautiful. Just as you and your neighbor might violently disagree over the artistic merits of a contemporary artist such as Damien Hirst, and I think these are out of order, but I think I have Damien Hirst somewhere. I think it's at the end. There we go. Yep, Damien Hirst. Okay, dead animals in a box. Different scientists find different aspects of science satisfying. Okay. Basically, I just had to have slides because I'm just used to that, but mostly don't pay attention to them. Like-minded colleagues and I prefer to search for underlying principles that illuminate connections among superficially disparate observed phenomena. Most of my string theory colleagues study specific solvable problems in which they use difficult mathematical formulations to tackle toy problems. Problems not necessarily relevant to any physical setup that might only later find applications to observable physical phenomena. Other physicists prefer to focus only on theories with a concise, elegant formalism that generate many experimental predictions that they can systematically evaluate. And others simply like computing. I mean, there really are different ways people do science. So whenever we try to talk about one single way, we're always going to get it wrong. Interesting principles, advanced mathematics, and complicated numerical simulations are all part of physics. Many scientists value all of them, but we choose our priorities according to what we find most pleasing or most likely to lead to scientific advances. The fact is, we often choose our approach according to which method best suits our unique inclinations and talents. Not only do current views of beauty vary, on top of that, as is also true with art, they evolve over time. Murray Gell-Mann's own specialty, quantum chromodynamics, which is the theory of the strong force that holds together the proton and the neutron, presents an excellent case in point. Gell-Mann's conjecture about the strong nuclear force was based on a brilliant insight about how the many particles that were constantly being discovered in the 1960s could be organized into sensible patterns that would explain their abundance in types. He hypothesized the existence of more basic elementary particles he called quarks, and proposed that these quarks carry a new type of charge. The quarks would then interact via the strong nuclear force that acts on this charge, and thereby bind together to form neutral objects, the objects that we actually find in the atoms, much as electrons bind with nuclei to form neutral atoms. If true, all the particles being discovered could be interpreted as bound states of these quarks, aggregate objects that carried no net charge. Gell-Mann realized that if there were 3 different types of quarks, each of which carried a distinct color charge, many such combinations of neutral bound states would form. And these many combinations could, and did, correspond to the plethora of particles that were being found. He thereby had found a beautiful explanation for what seemed like an inexplicable mess of particles. However, when Murray, as well as the physicist and later neurobiologist George Zweig, first proposed this idea, people didn't even believe it was a proper scientific theory. The reason is somewhat technical but interesting. Particle physics calculations rely on particles not interacting when they are far apart, so that we can compute the finite effects of the interactions that occur when they're close together. With this assumption, any interaction can be entirely captured by the local forces that apply when the interacting particles are in close proximity. The force that Gell-Mann had conjectured, on the other hand, was stronger when particles were farther apart. That meant that quarks would always interact, even when they were very distant. According to the then reigning criteria, Gell-Mann's guess didn't even correspond to a true theory that could be used for reliable calculations. Because quarks could always interact, even their so-called asymptotic states, the states involving quarks that are far away from everything else, were very complicated. In apparent concession to ugliness, the asymptotic states they postulated weren't the simple particles you'd like to see in a calculable theory. Initially, no one knew how to organize calculations among these complicated, strongly bound states. However, today's physicists think quite oppositely about the strong force. We now understand it much better than we did when the idea was first proposed. David Gross, David Politzer, and Frank Wilczek won the Nobel Prize for what they called asymptotic freedom. According to their calculations, the force is strong only at low energies. At high energies, the strong force is not much more powerful than other forces, and calculations work just as they should. In fact, some physicists today think theories such as the strong force, which become much weaker at high energies, are the only well-defined theories, since the interaction strength won't grow to infinite strength at high energy as it would otherwise do. Now, I realize that's kind of technical, but the important point is that at the time they made the theory, it didn't even seem like a legitimate way to do the physics, even though it seemed like it would work really simply. Gell-Mann's theory of the strong force is an interesting example of the interplay between aesthetic and scientific criteria. Simplicity was his initial guide, but hard scientific calculations and theoretical insights were necessary before everyone could agree on the beauty of his suggestion. This, of course, isn't the only example. Many of our most trusted theories have aspects so superficially ugly and uncompelling that even respected and well-respected scientists rejected them initially. Quantum field theory, which combines quantum mechanics and special relativity, underlies all of particle physics. But the Nobel Prize-winning Italian scientist Enrico Fermi, among others, rejected it at first. For him, the problem was that although quantum field theory formalizes and systemizes all calculations and makes many correct predictions, it involves calculational techniques that even some of today's physicists view as baroque. And that was the thing that Thomas said was just a minor thing at the end, when he was saying there's several different formulations. This is actually a big part of how to formulate the theory. And I think even physicists today would say it's ugly, even though it works in many ways. Various aspects of the theory are quite beautiful and lead to remarkable insights. Other features we just have to put up with, even though we aren't so enamored with their subtlety or beauty. This story has repeated itself many times since. Beauty is often agreed on only a posteriori. Weak interactions violate parity symmetry. That's symmetry that takes left to right. I mean, that sounds crazy. That sounds so ugly. But it's part of the model. This means that particles spinning to the left interact differently from those spinning to the right. The breaking of such a fundamental symmetry as left-right equivalence seems innately disturbing and unattractive. Yet, this very asymmetry is what is responsible for the range of masses we see in the world, which is in turn necessary for structure and for life. It was considered ugly at first, yet now we know it is essential. Although perhaps ugly in itself, parity symmetry breaking leads to beautiful explanations of more complicated phenomena, essential to all the matter we see. Beauty is not absolute. An idea might appeal to its creator, but be cumbersome or messy from someone else's perspective. Sometimes I'll be quite taken with the beauty of a conjecture I've come up with, largely because I know all the other ideas people had thought of before that hadn't worked. But being better than what came before doesn't guarantee beauty. having made my share of models that satisfied this criterion, but were nonetheless met with skepticism and confusion from colleagues who were less familiar with the topic my model addressed, I now think a better criterion for a good idea might be one that's even appealing even to someone who hasn't studied the problem. The reverse was sometimes true as well. Good ideas were rejected because their inventors considered them too ugly. Max Planck didn't believe in photons, which he thought to be an unpleasant concept, even though he initiated the train of logic that led to their conjecture. Einstein thought the expanding universe that followed his equations of general relativity couldn't be true, in part because it contradicted his aesthetic and philosophical predispositions. Neither of these ideas might have seemed the most beautiful at the time, but the laws of physics and the universe in which they applied didn't really care. So the next part is about beauty, and it's called Looking Good. Given the evolving and uncertain nature of beauty, it's worth considering some of the features that might make an idea or an image objectively beautiful in a way that has some universal appeal. Perhaps the most basic question about aesthetic criteria is whether humans even have any universal criteria for what is beautiful in any context, be it art or science. And I'd say that no one really knows the answer. Beauty, after all, involves taste, and taste is a subjective criterion. Nevertheless, I find it hard to believe that humans don't share some common aesthetic criterion. I often notice a striking uniformity in people's opinions about which piece of art in a given exhibit is the best, or even which exhibits people choose to go to see. Now, I know this doesn't prove anything, since we all share a time and place and a context. Beliefs about beauty are difficult to isolate from the specific cultural context or time period in which they originate. So it's challenging to isolate innate from learned values or judgments. In some extreme cases, people might all agree that something looks nice or appears unpleasant. In some rare instances, everyone might agree on the beauty of an idea. But even in those few cases, people don't necessarily agree about all the details. And sorry, I just have to take it aside, which was kind of funny. So I was visiting Oxford, and if you could go to the Ashmolean Museum there and ask them to show you some prints. So we went one morning and had them pull out prints. And one of my friends was extremely excited about The Apostles by Raphael, which is just incredibly beautiful. And sorry, these really are out of order. It's just an incredibly beautiful print. And it's very funny because we were talking to the person working there and said, he's just commented like how beautiful it is and how everyone thinks it's beautiful. And she turned to us and said, Grayson Perry didn't think it was beautiful. So, which I think sums it up. Even so, some aesthetic criteria do appear to be universal. In the beginning art class, we'll teach about balance. Michelangelo's David in the Uffizi Museum in Florence exemplifies this principle. David stands gracefully. He's never going to tip over or fall apart. People search for balance and harmony when they can't find it. Art, religion, and science all promise people the opportunity to access these qualities. Of course, balance might also be simply an organizing principle. Art is also fascinating when it defies our notion of balance, as we see in early Richard Serra sculptures, for example, which these aren't great pictures of them, but there's a lot of art that is really interesting precisely because it looks like it's going to tip over. It looks like it's off balance. Symmetry is often considered essential to beauty. Art and architecture often exhibit symmetry. Something has symmetry if you can change it, for example, by rotating it, reflecting it in a mirror, or interchanging its parts, so that the transformed system is indistinguishable from the initial one. Symmetry's harmoniousness is probably one reason that religious symbols often have it on display, and so I just have a picture of that. And they all do have some symmetry in them in these particular cases. More expansively, Islamic art, which forbids representation, relies on geometric forms, is notable for its use of symmetry. The Taj Mahal in India is a magnificent example. I haven't spoken to anyone who's visited the Taj Mahal and wasn't taken with its masterful orderliness, shape, and symmetry. When I was there, it was actually really fun because usually I don't get guides, but it was really fun in India because they don't have the same kind of regulations they have in America, so we just so one of the guides just took me to clamp around all places so I could see each symmetry point and see each symmetry in the reflecting pool and the light in the morning. It was really fantastic. The Alhambra in southern Spain, which also incorporates Moorish art and its interesting asymmetry patterns, may be one of the most beautiful buildings still standing today. And I talk about more recent art and cathedrals. But I want to say that art is often most beautiful, and I think this was also noted in the previous talk, when it's not completely symmetrical. Japanese art is notable for its elegance, but also for the well-defined breaking of symmetry. Japanese paintings look to have clear orientation that draws one's eye across the pictures. Simplicity is another criterion that might help when evaluating beauty. Some simplicity arises from symmetries, but underlying order can be present even in the absence of manifest symmetry. And this is something that I found quite striking, that Jackson Pollock pieces, for example, have an underlying simplicity in the density of paint, although the impression might at first seem chaotic. Although the individual drops seem completely random, his most famous and successful pieces have a fairly uniform density of each color that enters the work. Nonetheless, simplicity in art can be deceptive. So this is actually true, I once tried to just sketch Matisse cutouts, the cutouts he made at the end of his life when he was just not functioning as well. I thought it'd be simple. His simplest works, which he created when he was old and frail. Yet when I tried to reproduce them, I realized they weren't so simple, at least not for my unskilled hand. Simple elements can embody more structure than we superficially observe. In any case, beauty isn't found only in simple forms. Some beautiful works of art involve rich, complex canvases with many internal elements. Complete simplicity is, in fact, mind-numbing. We look at art, we prefer something interesting that guides our eye. We want something simple enough to follow, but not so simple as to be boring. And this seems to be how the world is constructed as well. So beauty and science. So aesthetic criteria are often difficult to pin down. There are unifying themes, but no absolutes. The same holds true when we apply them to science. Yet even though aesthetic criteria for science might be poorly defined, they are nonetheless useful and omnipresent. They help guide our research, even if they provide no guarantee of success or truth. Aesthetic criteria that we apply to science resemble those we use for art. Symmetry certainly play an important role. They help us organize our calculations and often relate disparate phenomena. And as with art, symmetries are usually only approximate. And I think that's a really important point, that we don't really have exact symmetries in nature. The best scientific descriptions frequently respect the elegance of symmetric theories while incorporating the symmetry breaking necessary to make predictions about our world. The symmetry breaking enriches the ideas it encompasses, which thereby yield more explanatory power. And as is often true for art, the theories that incorporate broken symmetries can even be more beautiful and interesting than those that are perfectly symmetrical. The Higgs mechanism, so I hope most of you heard about the discovery of the Higgs boson. A Higgs mechanism is the mechanism that the Higgs is the experimental consequence of, but the mechanism itself involves the breaking of a symmetry. And so the Higgs mechanism, which is responsible for elementary particle masses, is an excellent example. The Higgs mechanism very eloquently explains how the symmetries associated with the weak nuclear force can be slightly broken. Even before the Higgs boson was found, the theory was considered so beautiful, but more importantly, so uniquely satisfies criteria required by both experiments and theory, that most physicists believed it's realized in nature, and then it was discovered to be true. Simplicity is another important subjective criterion for theoretical physicists. We have a deep-rooted belief that simple elements underlie the complicated phenomena we see. When we propose ideas for what might lie at the heart of the standard model of particle physics, we usually become skeptical if the idea becomes too cumbersome. Only with a concise realization of simple and elegant principles do we expect an idea has the potential to be right. Again, as with art, physical theories can be simple, or they can be complex compositions made up of simple and predictable elements. More generally, the search for underlying scientific truth often involves searching for simple elements from which we can construct complexity. A starting point involving the fewest inputs gives us the most predictive power. The end point, of course, isn't necessarily simple, even when the initial components, and perhaps even the rules themselves, are. When we understand a phenomenon this way, we often view our characterization as simple and elegant. The most extreme version of such pursuits is the search for a unifying theory consisting of only a few simple elements, obeying a small set of rules. This quest is an ambitious, and some might say an audacious task. Clearly, an obvious impediment prevents us from readily finding an elegant theory that completely accounts for all observations. The world around us manifests only a fraction of the simplicity that such a theory would embody. A unified theory, while being simple and elegant, must somehow accommodate enough structure to match observations. We'd like to believe in a simple, single, elegant, and predictable theory that underlies all of physics. Yet the universe is not as pure, simple, and ordered as the theories. Even with an underlying unified description, a lot of research will be necessary to connect it to the fascinating and complex phenomena we see in our world. I'm going to skip some stuff. Of course, we can go too far in these characterizations of beauty or simplicity. A standard joke among students, which will be especially funny for people who were at the meeting yesterday, in our science or math classes, involves professors who repeatedly refer to well-understood phenomena as trivial, no matter how complex they might be. The professor already knows the answer and the underlying elements and logic very well, but this is not so true for the students sitting in the class. In retrospect, after they've reduced the problem to simple pieces, it can become trivial to them too, but they first have to discover how to do that. So the last part is called model building, which is what I do in a sense. In the end, just as in life, science doesn't just have a single criterion for beauty. We merely have some intuitions along with experimental constraints that we use to guide our search for knowledge. Beauty in art and science might have some objective aspects, but almost any application involves taste and subjectivity. For scientists, however, there is one big difference. Ultimately, experience will decide which, if any, of our ideas are correct. Scientific advances might exploit aesthetic criteria, but true scientific progress also requires understanding, predicting, and analyzing data. No matter how beautiful a theory appears, it can still be wrong, in which case it must be thrown away. Even the most intellectually satisfying theory has to be abandoned if it doesn't work in the real world. However, before we reach the higher energies or distant parameters needed to determine the correct physical descriptions, physicists have no choice but to employ aesthetic and theoretical considerations to guess what lies beyond the standard model. In this interim, with only limited data, we rely on existing puzzles coupled with taste and organizational criteria to point the way forward. Ideally, we'd like to be able to work through the consequences of a variety of possibilities. Model building is the name of the approach we use to do this. My colleagues and I explore various particle physics models, which are guesses for physical theories that might underlie what we see. Our goals are simple principles that organize the complicated phenomena that appear on more readily visible scales so that we can resolve current puzzles in our understanding. Physics model builders take the effective theory viewpoint, which I talk about in great detail and I can talk about later, but the desire to understand smaller and smaller distance scales very much to heart. We follow a bottom-up approach that starts with what we know, both the phenomena we can explain and those we find puzzling, and attempt to deduce the underlying theory that explains the connection among observed particle physics properties and their interactions. And just to be clear, the term model might evoke a physical structure, such as a small-scale version of a building, or that you might use to display it or understand its architecture. Or you might think of numerical simulations on a computer that calculate the consequences of known physical principles, such as climate modeling, or the spread of contagious diseases. But modeling in particle physics is very different from either of these definitions. Particle physics models do, however, share some of the flair of models in magazines or fashion shows. Models both on runways and in physics illustrate imaginative new ideas. And people initially flock toward the beautiful ones, or at least those are more striking or surprising. But in the end, they are drawn toward the ones that show true promise. Needless to say, the similarities end there. Particle physics models are guesses for what might underlie the theories whose predictions have already been tested and that we understand. Aesthetic criteria are important in deciding which ideas are worth pursuing, but so are consistency and testability of the ideas. Models characterize different underlying physical ingredients and principles that apply at distances and sizes that are smaller than those that have been experimentally tested. And the nature of model building in physics has changed according to the questions physicists have tried to answer. In the 19th century, physicists understood the notions of temperature and pressure and employed them in thermodynamics and engine design long before anyone could explain those ideas at more fundamental, microscopic level as the result of the random motion of large numbers of atoms and molecules. In the early 20th century, physicists tried to make models to explain mass in terms of electromagnetic energy. Though these models were based on strongly shared beliefs on how those systems worked, those models proved wrong. A little later, Niels Bohr made a model of the atom to explain the emission spectra that people had observed. His model was soon superseded by the more comprehensive theory of quantum mechanics, which absorbed but also improved on Bohr's bit core idea. Physics always involves trying to predict the largest number of physical quantities from the smallest number of assumptions. But that doesn't mean we manage to identify the most fundamental theories right away. Advances in physics are often made even before everything is understood at the most fundamental level. Models are a means of extrapolating from what is known to proposals for more comprehensive theories with greater explanatory power. They are sample proposals that may or may not prove correct once experiments allow us to delve into smaller distances or higher energies and test their underlying hypotheses. Our use of models admits the speculative nature of our ideas and recognizes the plethora of possibilities that might agree with existing data and explain as yet puzzling phenomena. And that's related to whether all of these things can be right. Not always, but sometimes. With models, we search for deeper interconnections and relationships that can address these questions. We use known theoretical ingredients and try to identify the potentially simple underlying ideas that enter what is ultimately a complex theory. I'm just going to skip some of this. So we don't know which, if any, of the different suggestions is correct until experimentally verified. Proposed models might be the correct description of reality, but even if they're not, they suggest interesting search strategies that tell us the distinguishing features of new, as yet undiscovered matter. Much of my current research involves thinking about new models as well as novel or more detailed search strategies that would otherwise miss new phenomena. I think about the models I made up, but also the full range of other models as well. Hopes are the Large Hadron Collider, among other things, will tell us the answers, no matter what they turn out to be, and we want to be prepared. So that's basically, so I go on to talk about the actual science it's doing, but I will give a little advertisement here, which is that this is all in this book. But I also, since this conference is called Truth and Beauty, I have to tell this, so I was just visiting the Institute for Advanced Study, and I don't know if you know this, but their motto or their symbol is like truth and beauty, and it has a picture of like two naked women, which is especially funny because the Institute is mostly men, in case you haven't visited. So it was really funny because one of my colleagues said, can you believe it? They're thinking of changing this motto, like, assuming I wouldn't care. And it's like, yeah, well, I said, I think they should. And he's like, really? I don't see the problem. I said, well, okay. I said, okay, you can leave it. Just change it to two naked men. And then he was like, oh, I guess I see your point. So I think that shows you that the notion of beauty is somewhat subjective. And as unfortunately sometimes seems to be the notion of truth these days. So I think I will just end there. Thank you.
Thanks a lot. The physics, I like this idea very much. Okay, let's enter the discussion, please.
Thank you. So first, lots of thanks, Lisa. Thank you for that. I want to suggest something that may elaborate what you said further. So suppose you think about the criteria for model building or for accepting a theory. You might say, I want a simple theory because I believe the world is simple, right? Mm-hmm. And therefore the simpler theory is more likely to be true. But you might also say, pragmatically, I want to choose a simple theory because if it works, well and good, but if it doesn't work, it will be easier to work with and get me to the next stage, right?
Absolutely.
And so now you might take the same approach to beauty. You might say, actually, if a scientist finds a particular conception of a theory beautiful, has a particular conception of beauty, and finds a particular kind of model beautiful, that might be conducive, this is an empirical question, to working further with it in ways that are fruitful and productive. So make the same strategy again. It's not that the world has that kind of beauty necessarily, it's just that that's a good... This is the last thing, and it comes to your point about the variability of notions of beauty. Actually rather a good thing for the scientific community if people pursue different strategies, right? Absolutely. And so long as you've got a diverse group of scientists with diverse conceptions of beauty, then this may actually be quite a good research strategy. Yeah.
So,
would you agree with that?
Absolutely. So I want to address each of those parts. So for simplicity, it's absolutely true. And so, for example, I have a dark matter model where I assume that there's an extra photon in the theory. That's a dark photon. And I'll get asked the question, like, why don't you consider like the dark standard model, dark weak force? And it's precisely because you want to be able to test things more easily. So it's not that you think this is necessarily the ultimate answer, but you want to have a clean enough system that you can check one thing at a time. And sometimes things only work when you put more together, but sometimes you need it to be simple. So one thing is, one thing is that you might, so you want to do it systematically. So I agree with that absolutely. As far as beauty goes, I mean, I think it's, look, I mean, I'm being cynical about the notion of beauty, but I definitely don't want to start off with an idea that I think is ugly. If I have to put in, but really when it really boils down to is economy. Because if I have to put in so many different ingredients, then I just don't believe it because it's losing its explanatory power. So the more I feel like I'm just fitting something, the less I believe it. And in terms of the notion of beauty being different for different people, I absolutely agree with you. And I think that that's really important. And it's just very funny because I think it's just people, I mean, if you saw the list of people talking there, it's people who had made big discoveries and then afterward wanted to describe their big discoveries. And of course, once everyone agrees on it and, it becomes part of the standard thing. I mean, it's like, Coca-Cola. I mean, it really doesn't taste very good. But, everyone drinks it. By the time everyone drinks it, and if you go to the World of Coke, which I happen to have done in Atlanta, they describe how it's the best tasting thing, and they really went out of their way to describe this. But it's just a really weird flavor. It has a lot of sugar in it, but it's weird. But we all agree that it tastes good after a while. And, and the same with beer. Most people don't like beer the first time they try it, but you all like it. And so I just think that it's just so simple to afterwards do that. And then the person who invented Coke says it was great. But it wasn't great. It's just that we all, get used to it.
In the same direction, let me give you another example. I showed several times these epicycles, the Ptolemaic epicycles. I mean, both the Copernican and the Ptolemaic system, they both work. And one might even argue that the Ptolemaic epicycles look these Rosetta, they look nicer. I mean, it both works. It's up to you. So, yeah.
I don't think anyone thinks the Ptolemaic system looks better.
But
but actually, my favorite one is, I forget the one who did that, but there was one who did something in between. Iconic. That was my favorite one with the Earth and everything else rotating around it. So that way you could satisfy the church and you could have the Earth in the center. And that's really ugly. So I think it's, I do think that, and again, I think the problem with that isn't just the beauty idea. It's just that you're fitting things. It's not, no one can predict anything. Whereas the other case, you have simple ellipses, and then you can do more complicated phenomena that people have done since then.
Okay.
Thank you very much, Lisa. My question returns to Kostek's query about beauty having survival value this morning. And in this case, the survival of scientific theories. It often takes an enormous amount of fortitude, perseverance, not to mention time, intelligence, and resources to actually come to grounds with a theory. I'm thinking, for example, of the missing solar neutrinos. And this is a theory, a beautiful theory, I thought, anyhow, by Hans Bethe about the creation of ever more heavy elements in the interior of stars over time. And the problem was it predicted a certain number of neutrinos that ought to be observable from Earth. And it took a very, very long time to find these. I can remember as an undergraduate in astronomy courses, descriptions of empty boron mines in Utah devoted entirely to this purpose. It strikes me if this had been a theory which had been in some way, however defined, less beautiful to the astrophysicists, they would have given up long ago on this. So
there's a
that's
really interesting
simply
story
to pursue Kostek's idea.
So there's actually two aspects to that theory, which is really interesting. So one is the creation of heavy elements, which required to overcome some energy barrier. So you wouldn't have been able to get to the heavy elements. So I'd say the one aspect of it was that there was just no other explanation. So if there really is no other explanation, then you're going to stick with that one until something else comes along. And it's true, and it really wasn't. And so the sense in which it was beautiful was that it was an explanation. There was no other way to get to those. There was an energy barrier. You obviously had to have something that created a lot of energy. So I'd say it was really, if there had been alternative ideas, then people probably would have been less likely to stick to it. And in reality, if there were simpler ideas, maybe it's like there's no such world, so I can't really argue this. But I mean, the reason there were no simpler ideas was this was the right one, you know. So it wasn't it's not so crazy.
With 20/20 hindsight.
Right. No, but it was. But that's the point. There really were no alternatives. And so sorry about that. So the other thing that was really interesting about that, excuse me, sorry about this, was that they didn't discover the neutrinos. And there's another really funny puzzle there, because people looked for what are called solar neutrinos too, so that was from supernova. But the solar neutrino story is also really interesting, because there it really was a complicated model of how the neutrinos would be emitted. So neutrinos are these almost massless particles that are neutral in the standard. Well, they don't carry charges, so they're really hard to see. Thank you. So basically, they didn't see them. And at first, they really didn't see them. They saw none. And solar physicists were so confident in their calculations that they said there has to be something interesting going on. Like neutrinos have to have mass, and they have to turn into each other. And, you know, those of us who were not astrophysicists thought, you've got to be kidding. You trust your theory that much? And and then they finally did some work, and then they found half the number of neutrinos they were looking for. And they still said they had the explanation. We're like, okay, come on, you know, your experiment wasn't working before. It's probably still not working now, and you know, eventually you'll find them all. And they turned out to be right. So, you know, and I mean, in some sense, the most beautiful explanation there would have been that, you know, they were looking correctly, or they hadn't found them yet. But it turned out there all these complicated calculations and this theory of mixing, which isn't particularly beautiful or not beautiful, it's just what it is, was right. So we don't always get it right. And I think, you know, some of us, I mean, it was definitely a worthwhile pursuit to look for those neutrinos in that case, but we didn't think that their theory would turn out to be right, and it turned out to be right. And it was even more interesting because it wasn't just a simple mixing. It really had a very tuned value that corresponded to mixing inside matter that gave you exactly what they found. It really was very detailed. And, you know, our aesthetic criteria is usually that anything that needs these kind of that much level of detail probably isn't right, and it turned out to be right. So it's an interesting story too.
Right.
Listening to you, I found a similarity between my field, art history, and the natural sciences, because there seems to be the common interest in theories of representation. We first learned that it is about mirroring. Of course, the mirror is an important icon for realism, or reflecting, or depicting. So creating something parallel is exactly the goal of various works of art. Now you introduce the term model, and I wonder whether we are making a leap here, and whether model is a different form, which doesn't sound as realistic as the other terms that you introduced. And the model, I wonder, is it, of course, a question of scale, but also it seems to be more creative, again, coming back to the polarity between, or tension between creation and discovery. You have to create something in order to discover, and the model seems to be something intermediate.
So it's a really interesting thing, and it comes up when we're actually writing our papers. Because, you know, my colleagues, you know, after having written popular books, I'm very careful about my wording. And so my colleagues will say things like, we add a new force. And I'm like, you can't add a new force. Who are you? You know, but that's how it feels. It feels like you are adding a new force. So it feels like you're creating something. But what you're really trying to do is come up with something that matches what's really out there. So in some sense, you know, I think most people would say, you know, they might talk about the inventor of the Higgs mechanism. But in reality, in some sense, he discovered the Higgs mechanism. Because it's not, you know, it was there. And it is sort of a philosophical point, whether you consider it something there to be discovered, because certainly the act of doing it feels like you're creating something. But what, you know, if you really think you're doing science, you really are trying to discover what it is that connects these phenomena.
Real quickly, the reason the two naked ladies are the Institute logo
Yes.
is the 18th century notion of uncovering nature.
Right. It's just I think nature is both sexes.
Well, no,
It's she.
Yeah.
Not the
Yeah.
argument, but in other words, this
Who
notion,
defined that?
you know, this notion of the fact that nature nature is out there, and what science does is to uncover
That's
it.
really right.
Right.
That's exactly right.
You know,
No, it is a really interesting, I mean, it is an interesting question because as people, we do feel like we are inventing things.
yeah.
We feel like, and I think, the book on Humboldt was, called The Inventor of
Can I help
Nature.
you?
No, it's okay, thanks. It was called The Invention of Nature.
Yeah.
And so, in some sense, we are defining the categories, we're defining how to do it, we're figuring it out. So we are doing something, but in some sense, and, that's a little bit, the way, Einstein with his Spinoza stuff is kind of eliding the whole thing. It's like, there's this stuff out there, there's this order, and we're just trying to find it. It's a way of sort of humbly elevating yourself too, right? It's like, you're talking to God, you're finding out what nature is. So it's really a description of the process, but it is funny though, because the words that you naturally use when you're doing it are things like, we'll now put a new force in, we'll now add these particles, we'll now, it feels like you're doing something, but, that's not really objectively what's going on.
Just very, very brief on the word of model. That's we should really rename it by theory. The standard model of particle physics is a theory. I mean, model
No.
should.
Actually, so I skipped that part, but there's actually I actually would argue that there's a difference between theory and model.
Yeah.
So a theory is sort of the whole description of how we would do it. But a model, so I sort of use the analogy, it's like there's general things of making a cake, but you can make a specific kind of cake, You can make black forest cake or whatever. You can put in different ingredients. So they would all be theories. They're all the same theory. They're all field theory or general relativity.
Yeah.
But they're different models because they're different forces. There's different specific forces. So we call it the standard model. But the standard model refers to a particular quantum field theory with the strong force, the weak force, the electromagnetic force, quarks and leptons. If we add other particles to it, we call it beyond the standard model. So it's a new model that underlies it, that describes it. So, but I do think that there is a trickiness in the way we use the word theory and model, because people think it's less predictive or less definite than it is. But theory and model, I would say, are different.
Yes, and in this spirit, I find standard model, at least in particle physics, not very appropriate. It's historical. Okay, for cosmology, one could argue, since in cosmology we have a lot of parameters which may be artificial or environmental, like the Hubble constant and the matter content and so on. These are just crazy numbers. But for the
Well, but the quark masses and mixing angles, I mean, those are crazy numbers too. I mean, that's the point. I mean, there's some beautiful elements, and then there's some really ugly stuff that we don't understand. It's just the way nature is. Yes.
Just a very quick question to what you just said. If you're building these models, and you say they are within one certain theory, but you're building different models, to what point can you add things and it becomes a different theory?
That's a really interesting question, and I don't. And quite honestly, I think it's a little bit slippery when we call something a different theory. I'd say that there are sort of big so-called quantum leaps. In fact, I mean, it's called a quantum leap for a really good reason. It was an entire different formulation of physics. We actually don't talk about like a relativistic leap because it is working within the same structure, but I would say that it's a different theory in the sense that it's a whole different way of calculating things, your basic ingredients. So let me slow down a little bit. So then we go back to the notion of effective theory, which is something I mentioned. And it comes up in lots of different contexts. And effective theory says, these are the things I can measure, these are the rules I can use to relate them. So Newtonian physics said, I have a ball, I have a position, a momentum, and I can predict what happens when I throw the ball. Now we now know that's not the fundamental description. It's made up of atoms. We also know that if it went near the speed of light, that would be the wrong physical description. So there's another theory that underlies that one, based on quarks, or based on atoms, or based on relativistic principles, which is another one, that I would say is a different theory, because just the very objects that I'm using to describe what I'm going to measure are different. And so and the physical laws are different. The thing that's interesting is that they're all compatible. So in answer to the question that you asked during your talk, Could string theory and supersymmetry and extra dimensions all be compatible? In that case, they can be. They're all different aspects of the same theory, but you might focus on one or the other. But probably I would still refer to them as models. But I would call string theory a theory, but things that I derive from that I might call models. So even if I had extra dimensions of space, so you might think that's very different, it's still the same basic physical laws and the same ingredients at some levels, so I would call it a model. So, yes.
Yes.
Just on that, I was struck by two things. How many times you said, but it turned out to be right? And on the other hand, on this discussion about modeling and theory, at which point we know that a theory is true, or that what we have is truth capital, right?
Okay.
And whether we shouldn't rephrase the title of this conference, Hypothesis and Beauty?
Okay, so I really like that question. So the first one, the answer to the first part is, as you know, history is written by the winners. So I talked mostly about theories that we still talk about. I could talk about a lot of theories that were then proven wrong, but I didn't mention them. Okay, so because most people wouldn't know what they were, as probably not everyone knew even the ones that are right. So I didn't mention those. But in terms of your question, it very much ties into the notion of effective theory. So in effective theory, we test the idea model. And I think Philip said earlier, it works for many different things. So you test it in many different ways. But usually there's a prescribed range of parameters for which you've tested it, which are the ones that you can afford to get to, basically. A certain energy, a certain distance, a certain speed. There's parameters that define a certain density. There are parameters that define the regime in which you've tested it. But so you test it at some level of accuracy. So basically you can say, I believe this at a certain confidence level. I believe this at 80%, 90%, 99.99%. Now what's really interesting about that, you're absolutely right, there is no absolute truth there. You're saying, but it works in the regime that it works. Okay. But that extra 0.001% tells you how wrong your theory can conceivably be. And that could correspond, for example, to the underlying theory aspect that I said before. So an effective theory is important not just because it's practical, but it's also telling you something about what the underlying truth with a slightly bigger T can be. So we're never getting to the ultimate thing, but we're getting to more and more accurate things at some level.
So, last question, please.
Thank you for the lecture. And I think the overall impression that I had is the history of physics, the history of biology. And looking at the book cover and hearing your lecture, I wonder whether it is really the results or the formulas that we deem to be beautiful, or the journey or the story we tell about getting into those formulas.
Well, honestly, it really depends who tells that story.
Yes.
Just like all other stories.
But I think even the words that we pick, how quarks become a word, how DNA become words even. For many people, it resonates, I think, because in the sense of...
So I think the fair statement is that when we have a good theory, we usually can tell a good story behind it. When you're actually doing it, those guys were probably, scratching their heads. When people found quantum mechanics, really, they didn't want to believe it. It just shouldn't be right. It was just so crazy that you had to abandon the fundamental ideas upon which physics was constructed. So there were many days of people tearing out their hair. Now, you don't, you do read that people didn't believe it. You read some nice stories and some nice quotes. But there's a lot of nitty-gritty stuff that goes into getting things to the point where you can tell the nice story. So I think in the end, you do have a nice packaging of it. And like everything else, that packaging covers up a lot of stuff that was going on. And there's nothing wrong with that. That's how you make progress. You make mistakes. You figure it out, you make mistakes, it works. And I think sometimes when we tell this, and I think the problem is, people are so afraid of admitting uncertainty because that's just taken as a weapon against you these days. But, and that's why I think people are so, people are afraid of ambiguity. They're afraid of saying, we don't really know this answer. And it's true. It's certainly politically, it's used as a weapon. And, I realize it's not about politics. But it is used as a weapon, and it's considered a sign of weakness in some cases. I think scientists, on the other hand, you know, in many cases, view it as a really good thing when people say, I don't know. Because it doesn't mean you won't know forever. It means that we really are trying to figure something out.
Okay, thanks a lot.